Okay, welcome to lecture of week number 8. We are going to talk today about mobile robot navigation and some discussion about fuzzy logic control, mostly in real-time hardware applications. As you may recall that I had mentioned many times before that a mobile robot resembles a blind person. Meaning that a blind person, unfortunately, doesn't know where he or she is in a complete darkness and where he or she needs to go after that, how to take the next step. So, taking steps for the mobile robot is navigation, which is chapter 5 of your book. Where you are located is localization, which is the next chapter. So, as far as this chapter is concerned, we're assuming you know where you are. We just want you to move. Next chapter, we'll add that to it. Okay, let me now go to chapter 5. You may remember that back in the 1980s or 1990s, the company called iRobot, which was the brainchild of a bunch of professors and students from MIT. Rodney Brooks was one of them, and they put out a robot which would go to your living room and clean the floor. What you see here is a completely random path planning and navigation for a Roomba cleaning your floor, and all those shiny lights are the tracks of the robot, which goes and hits the wall and goes somewhere else, hits for example, the table and goes somewhere else, just moves around and around and around until the battery is dead. And you don't even have to be home. You can set it up and go to work. You know, one of my children had that in his house, okay? And of course they needed to do it that way because otherwise it would have been a very expensive product for people to buy. As of 2011, 5 million of these robots have been purchased, including the one that we have in the ACE Lab, number 1, that Patrick had put additional manipulator on top of it. So they are not really ready. So this also resembles the navigation of ants and bees, which have very few neurons in their brains, and they cannot afford to mark the whole surrounding for those species. So this is more or less resembles those species than a well-defined and well-planned navigation map. There came Italian-Austrian neuroscientist Valentino Breitenberg, which actually published a paper, or a book rather, Vehicles, Experiments in Synthetic Psychology, in 1986 with MIT Press, where he described reactive goal-achieving vehicles, which are known as Breitenberg vehicle. And Breitenberg vehicle is an automaton or robot which combines sensors, actuators, and their direct interconnection to produce goal-oriented behavior. Okay, this is essentially what the subject of that. Now, Gray Walters was an American, came up with tortoise, a turtle type of which predates that particular book, and use this term, but it nevertheless is an example of such a vehicle. So independently, Gray Walters actually came up with the same kind of vehicle, like which several years ago Breitenberg came up. In fact, if you see down below, here is Dr. William Gray Walter, who was born in Kansas City, and that was the span of his time. So the idea is now basically fits into the basic definition of a mobile robot, which in fact it is also more or less relevant to manipulate a robot. You may remember in the manipulated robot we defined it as a programmable machine which can work like a human, mostly like human arm, and it's attached to the floor. But a more general one is a robot is a goal-oriented machine that can sense, plan, and act. Okay. So what we are talking about in this chapter is planning. Okay. You need to plan to be able to move from point A to point B. So Breitenberg vehicle, in fact, is a very simple class of goal-achieving robots, and they're characterized by direct connection between sensors and motors. So you use the information from sensor. Based on that, you decide how to move, thereby activate your actuators to move from one point to another point. For doing that, the robotic toolbox has created a model, Simulink model, called S1_Breitenberg, which is shown here. This vehicle has the basic bicycle model that you already have seen in previous chapter. That hopefully you are working on your homework number 3, where you're going to be using that. As you remember, the outputs of the inputs are the velocity and orientation, or the gamma angle. The outputs are x and y location of the bicycle or the vehicle on the ground, and the orientation theta. All three variables are going to be going into two different sensors, one on the right, one on the left side of this Breitenberg vehicle. And then you look at the differences between number 2 minus right sensor reading minus left sensor reading. That arithmetic becomes clear in a few minutes. And then you will have the difference between the right and the left, which will allow you to actually come up with the right orientation here. Okay, and this difference that I just told you is a gradient, a difference between where you like to go and where you are right now. The velocity, the velocity of the bicycle is being fed back from right here, as you see. So there is an equation, velocity equal to 2 minus sensor value from right minus sensor value to the left. When you reach your goal, SR and SL will be identical to 1 according to this equation. If you have x minus x goal is equal to 0, y minus y goal equal to 0, so you have 200 divided by 200, which is 1. Okay, so at that point, you have 2 minus 1, velocity is 0, which is what you want. When you reach the goal, you have to have 0 velocity. You have to stop. And the difference, therefore, this difference is an indication of an error or a gradient of the error. And what you are feeding back is the proportional of this gradient, which is indirectly similar to a derivative controller. Okay, it looks like a proportional control, but the kind of signal that you're feeding back is proportional to the derivative. Okay, very similar to the inverted pendulum, for example, when you have the two velocities fed back through the sensor directly. So proportional feedback of a 4 degree of freedom, not rather 4 state variable pendulum is really like a PD controller. So the steering angle is going to be gamma obtained from this feedback right here, where you have the difference between the two sensors, and the velocity is going to be 2 minus SR minus SL, which is fed back here. So you have two feedback loops here. One is for the steering angle, one for the velocity. And that's what you need, because those two are your inputs. Okay. So this is a Simulink model for the Breitenberg, which derives the vehicle toward the maximum of a provided scalar function. The vehicle plus controller is an example of that kind of vehicle. So, for example, if you have goal to be x to be at coordinate 60 unit, let's say 60 meter or 60 centimeter, and yc is at 90, then this equation is a measure of the velocity coming out of the sensor, or the orientation, gamma, rather theta. So the peak value, the particular function has a peak value at the point 60 and 90. In other words, based on what we are talking about in these two control paradigms, it's equivalent to maximizing some kind of a scalar function, which is the negative of the distance of the mobile robot and the goal. So let's look at figure 5.3. Figure 5.3 shows the path of Breitenberg vehicle moving toward and past the maximum of a 2D scalar field, whose magnitude is shown in color coded. So when you are here in the blue area, you are far away from your goal. So it's blue and has a very small sort of function, cost function, a scalar function. As you move closer to the goal, this value keeps going up. And when you reach sensor value of 1 for each, you have 2 minus 1 equal to 0, which you are reaching here. Now, Breitenberg's vehicle, the model that we are looking at right now, has one shortcoming. And that shortcoming is that inherently built into that model, there is no obstacle avoidance. If you have something in between the path, that by itself is not going to work, because it will run into obstacles, doesn't see it. okay? Because those sensors are not looking at like an image or some kind of proximity sensor, this kind of, okay? At the lowest level of a hierarchy of control paradigms, there is an echelon of different control philosophies. At the lowest level, the mobile robot goes through what we call primitive behavior. What are primitive behaviors? Primitive behavior is to avoid an obstacle or follow a wall. Okay? And at the next level, you have combined or compound behaviors, where one or two or more of these primitive behaviors are combined to come out to be a more meaningful navigation. Okay? And then at the very end, you could have some kind of global goal where you can put a whole bunch of behaviors combined together. Okay? So, in the 1980s, or was it 80s? You know, it was in the 90s, my students in previous university, they actually put hierarchical behavior control for a mobile robot, where they programmed in fuzzy control and in genetic programming. They combine those two tools to design an intelligent controller for a hexagonal mobile robot that they built. The students built it themselves also. And they were able to extend Rodney Brooks at MIT's behavior control for CRISP rules, expert rules, extended to fuzzy logic rules. Okay? And they went to Toronto to do a competition internationally. They didn't win anything, but they did go there. Okay? So, therefore, this behavior control is a discipline which is very relevant to mobile robotics. All right. So, and this is called behavior-based robotics. Okay, there we go. Right. And they are complex, and some might say intelligent-looking behaviors can be manifested by such systems. Okay. Okay. Another simple automata for mobile robotics is another class of reactive robot known as bugs. There are simple automata that perform goal seeking in the presence of non-derivable areas or obstacles. This is essentially similar to what iRobot and that Rombo does. And they are also similar to Breitenberg's class, which you can see here. And the bugs include a state machine and other logic in between the sensor and the motor. In the classical logic, there is a subject called a state machine. State machines are a set of rules where you can write as a piece of extended software, which you can use it to design and construct, actually build something. Okay. In the 1960s, where computers were very, very primitive, they used artificial intelligence for actually creating expert machines. And for example, they would have, there was a company in Massachusetts, Digital, called Digital. Probably none of you remember it or anything like that, or heard of it even. And they were putting out middle-sized computers called PDP, PDP-8, PDP-11, PDP, and so forth. Of course, they're now far gone, that company. But they were using artificial intelligence to design their computers. And it was extensive amount of code, thousands and thousands of lines of code that they would put with expert rules of artificial intelligence, which has crisp or classical logic behind it, which is what? 0 and 1. Yes or no only. And it didn't go too far for the following reason, that if you have a bug in one line of those 10,000 code, the whole thing falls down. Okay, that was the problem. In fuzzy, you have infinite levels of logic. You can afford to make mistake several times, but you still can do something which may be good enough. Okay? So, the package also has created a command called map1, which gives you a 100 by 100 matrix variable or a map in the workspace. And the elements are 0 or 1, representing free space or obstacle. If it is 0, that means that particular cell, if you will, that particular cell is free to navigate to. If it's 1, it means something is there. Some obstacle is there. Okay. So figure 5.4 looks like this. This is your map. Okay. And this map, as you see, has a whole bunch of red parts. They're all obstacles. Okay. And bug 2 starts at a point. It starts at a point, I believe. Well, first of all, the goal is 50 and 35 for bug 2. That's 50 and 35. That's your goal right here. And your initial value could be right here or here, doesn't matter. So somewhere here is your initial value. Okay. In fact, here you have path from 20 and 10. 20 and 10 is right here. Okay. So what you see here is that this is your initial point. You want to go there. Obviously, the best way to go is go directly through there. But as soon as you come and hit this obstacle, this structure, you can't go any further. So one way is to just follow the wall, follow the walls of this obstacle. And then you go all the way here, you go up, down here, down here, down here, then you follow it, go to there. That's one way to do it. It's not going to be the optimum, but that's one way to do it. Now notice that you could also have done it faster by going through here, like this, and then find a way like that. That's another way you could have done it. Okay, so in order to run the bug 2, you create your map, and the way you create your map also is given here. Take a look at this. This square part of the text is how to create your own map. Okay. In one of our future homework, you will be using this particular map as is in the book, but you can also use this argument here to build your own map. Okay. What we may do in that homework, we may give you a pictorial representation of a map which corresponds to the floor of ACE-Lab, which your experiment number 3 has to be done on it. So you can have you can do some simulation of the experiment before you do it in real time. Okay? And this is the kind of approach that you know we are pursuing. You recall your homework number 1 was simulating inverted pendulum. Now you do the experiment. Okay, so therefore you put simulation, you run it like this, bug, point, path with the initial location vector of x is 20 and y is 10, which is right here. And then you extract, put the output of it into a matrix, P equal to bug, point, path, 20, semicolon, 10. And when you say what is P is all about, is a double precision matrix 332 by 2. So what is that 332 by 2? That's a 2 by 2 matrix. It has 332 rows and 2 columns. Column 1 is X, column 2 is Y. This 332 point is nothing but these green points you see here. That's what they are. Okay? Every point corresponds to one line of that matrix. Okay. And then you plot it. Okay. And then Bach-2 algorithm has taken a path that is clearly not optimal. As we said, it has wasted time by continuing to follow the perimeter of the obstacle until it rejoined its original line. It would also have been quicker in this case to go clockwise. As I said before, you could go the other way. Instead of that way, you go the other way. Around the obstacle. Many variants of Bach algorithm have been developed, but while they improve the performance of one type of environment, they can degrade performance in others. Fundamentally, the robot is limited by not using a map. It cannot see the big picture and therefore takes paths that are locally rather than globally optimal. So this is an important point. All these things that have been given to you, this Breitenberg vehicle and Bach algorithm are free of map. It is not using map. You see, map is very important because every robot needs to know what is all around it. Okay? And map is the objective for that. So, therefore, we move into map-based planning. The key to achieving best path between points A and B, as we know from everyday life, is to use a map. Of course, GPS is something that we are all getting addicted to. Okay? And we no longer know how to go without it, and we lose sense of direction. I'm not an exception to that rule. So typically best means the shortest distance, but it may also include some penalty term or cost related to traversability, which is how easy the terrain is to drive over. It might be quicker to travel further, but over better road. A more sophisticated planner might be considered, also consider kinematics and dynamics of the vehicle to avoid paths that involve turns and are tighter than the vehicle. The vehicle can execute. So, let me just, my time for this session is almost done. I just want to let you know that I was briefly involved with the Mars mission number 1 in 1990s. Mission number 2, which never was able to land on Mars, was a gigantic mistake of Lockheed Martin, which cost the taxpayers almost $1 billion. Nobody made a very big fuss of it because I was inside it. I could learn about those things at the time. And the mistake was that the company mixed British units and metric units in their design. And nobody actually, up to date, nobody knows what happened to the vehicle. And then, of course, let me just finish this because we are in the middle of a story that is interest to you. Then the next one was that the vehicle went close to the Mars but was not able to survive because of the rocks and other things underneath. So they used, believe it or not, fuzzy logic to classify the rocks on the surface of Mars to determine the traversability of the vehicle. Okay, that was done at Jet Propulsion Lab. So let's take a few minutes and then we'll start again.